and I'm from UC San Diego. In this work, we present a real-time method for process 3D hand pose tracking using capacitive touchscreen, and demonstrate how our method improves the experience of remote whiteboard interactions. Touchscreens enable users to interact naturally with digital devices via stylus or hand fingers. They are widely used as virtual whiteboards in remote communications. However, the speaker's hand gestures are not visible to the audience, which reduces the efficiency of interaction and immersive experience of remote communication. A lot of methods have been proposed to address this issue. However, these methods require additional cameras installed on top of the screen to capture hand pose, which limited the application scenarios. Since the touchscreen is everywhere, we aim to explore visualizing hands on a whiteboard using only touchscreens, allowing our method to work on most daily devices without extra equipment. When the user's hand contacts the touchscreen, the raw capacitive image of the touchscreen can reveal hand gestures. We developed a method for real-time 3D hand pose tracking using the raw touch frame sequences. On most daily devices, without extra equipment, our method enables the speaker's hand and pen to be visible on the touchscreen. The visualized speaker's hand and pen enhances audience engagement. Now, let's dive deeper into our approach. Here is an overview. When hands come into contact with the touchscreen surface, a real-time capacitive image is generated, highlighting the areas being touched. Our method takes the latest capacitive image from the image sequence as input. The joint position estimator employs a deep learning-based method, incorporating temporal information to predict hand poses and outputs the current 3D joint positions of both hands. Following this, the constraint inverse kinematic solver reconstructs 3D hand poses based on the 3D hand joint positions and outputs the 3D hand mesh of the current pose. We use a neural network to estimate the joint position of each hand in the touch image. For a given touch image of the current frame, the algorithm first determines the existence of each hand within the image and subsequently predicts the 3D coordinates of each joint. To enhance accuracy, we employed a heat map and depth distribution for each joint, which has been demonstrated to be more accurate than directly predicting the coordinate values. For optimal performance in learning-based hand tracking on touch screens, we capture high-precision hand pose data that is accurately aligned with the touch screen. Our system captures hand images from different views with 9 RGB cameras and reconstructs hand skeletons using multi-view stereo techniques. The hand skeleton is aligned with the capacitive images captured by the touch screen. In this way, we created a high-precision touchscreen-based 3D hand pose dataset. In some challenging scenarios, our method can handle situations where hands are located on the edge of the touchscreen. Our method can predict accurate results even when the contact area between hands and the touchscreen is small. Our method is robust to situations where hands are close to each other. We compare our method with the most related work, touch pose. In the case of fingers tapping the touch screen, sometimes only one finger is on the touch screen. Based on the temporal information, the result of our method is more accurate and stable. Different from touch pose, our method further allows both hands to touch the touch screen at the same time. We gave two exemplary applications of our method. First, we developed a whiteboard prototype system. Our system can simultaneously estimate the gestures of both hands, enabling the speaker to perform operations directly through gestures. The speaker can perform actions such as zooming, shifting the canvas, and erasing using a fist. In this way, we offer a more convenient method for speakers to operate on the whiteboard. When the speaker draws on the touch screen, the drawing content is displayed. The speaker's hand and pen are also visible. In this way, we enable the audience to observe the speaker's writing process, enhancing the overall visual experience. The whiteboard is transparent glass panel illuminated from the edges, allowing presenters to write while facing the audience. It enhances engagement, improves content retention, and provides a visually compelling way to present information interactively and clearly. We developed a whiteboard application based on our hand tracking method, which allows the speaker to draw contents on the screen while facing the audience. When the speaker draws with the stylus on the touch screen, his eyes are also concentrated on the drawing point. The feature provides an engaging experience for the audience. Enhanced by our hand tracking method, the speaker can directly point to the screen with their fingers. Furthermore, our passive deformation effect simulates hand touching the screen. And there are some future works. We believe in the future, the touch screen can be everywhere in our daily life. And if we can improve the if we can build a realistic hand appearance, and it can improve the immersive communication to users. Also, we want to support multiple users to use our application so that it can be used in more applications. And that's all. Thank you for listening. And please visit our website for more information, like the code, model, and the dataset. Thank you.
One question from the audience.
Hi, a very interesting talk. My question is about design aspect. Do you imagine this is an always-on function? Or like, do you, if not, how would you provide users to switch on and off this feature based on the context?
Sorry, can you repeat it again?
Oh yeah, so do you think like these features should be always on? Like whenever users use like touches the display, this would always appear. Or like based on the context, sometimes users just want to touch without like wanting to show this visualization. And how do you switch the on and off of this feature?
Oh yeah, we considered this question before, and we did a user study. And the users found that sometimes in the whiteboard applications, if we display the hand on the screen, it can make some occlusions to the words, and it will influence the understanding of the content. So I think it would be better to offer an option to the users, like a button. If the user touch the button, the hand will disappear. And if the user touch the button again, the hand will be recovered. So the user can switch between different modes using a button. Or for some applications, we can also let the user to adjust the transparency of the hand. It can be not a solid mesh, but transparent, and the hand can show some clues during the illustration, but the transparency allows the audience to observe the words behind the hand.
I like the idea of changing transparency based on the context. Thank you.
Thank you.
Thanks, Xinsheng, once again.